I think I wrote most of it down anyway. Like I was
Alrighty.
solving it while you were going.
We'll hammer that out real quick before we get into the math.
Okay, yeah.
Okay, so I got the recorder on, and I will just go ahead with today's presentation. Today's presentation does not have slides like the previous one because it's very hands-on. It's also based on C and C++, but I won't get too far into C and C++. Okay, so for those of you who have not been programming using C or C++, this is kind of like a preview of what you'll be doing because I think most of you will eventually take CISP 360 and so on. Okay, so the first thing we'll do is we'll go take a look at a few library subroutines, okay, the description. And one of those is called getS or getString, okay? And the man page, is, this doesn't show really well, but this is the most I can zoom in without, forcing it to, break up the lines, okay? So I'm not sure what to do with this. Let me see if I can change the intensity. So the preferences for the colors, can I change? Yeah, the text color is already maxed. Huh, sorry? Far right. Black and white. Is that better? This is the problem is with the projector itself. The lamp is going out, so that's why the intensity is not nearly as good as what it should be. Is that better?
Yeah.
Okay. All right. So we'll just choose this one until it doesn't work. Okay. So this is a fairly easy subroutine to understand. What it does is it is going to get a string from standard input, and when you look at the parameters, all it is asking for is a pointer. It is asking for a pointer to some location in memory and say, okay, give me the location. I will go to the standard input file, grab whatever is there, and stash it over there. So the first big question is, how many bytes are you going to put into that location? It is not specified here. In other words, the programmer has to make sure that the input doesn't have more characters than the array that is already allocated to store those characters. Okay, there's no number passed to get as a gate. Okay, up to this many characters. It will grab as many as possible. And that's why in the description, the first thing you read is what? What does this say? Never use this function. Okay? And that's because, once I highlighted it, it's hard to read, but that's the part, okay? Because this is the main reason why we have security flaws, okay? People who use functions like this, string copy without the end, that sort of thing. But this is by far the worst of them because it's so easy to use, and people use it to grab something from the input file. Okay, so the description is pretty simple. Okay, I'm just going to read it out loud. It reads a line, okay, so it's sensitive to the line key character. It reads a line from standard input file, stdin, into the buffer, pointed to by a pointer, which is parameter s in this case, until either a terminating new line or end of file. So it will terminate, it will stop as soon as it sees a line key character, which is ASCII 10, or end of file, which means there's no other stuff to read in the file. Because otherwise, it would keep going, which it replaces with a null byte. So the last byte here, which is likely to be just the line key character, is going to be replaced with a null byte, which is an ASCII 0. No check for buffer overrun is performed, and that is the main reason people should not be using it. The return value is not that important because it just returns back whatever the parameter is, so that you can chain the calls without using multiple lines. Okay. All right. So what we'll do today is we are going to take a look at programs that, despite the warning, decide to use this function call, and then we'll see what happens. Okay. So we'll go ahead and write some simple programs. I will just put it into the temp folder, and we'll say get string.c. Doesn't have to be CPP, just C is fine. So include a header file, and here's my main function. I'm not going to be using getS in the main function because eventually I want to show you guys how you can exploit a function or exploit a program like this. So I'm going to call another subroutine. We'll just call f here. And to make the compiler happy, return 0. And now we have function f, which doesn't really take any parameters. And then inside here we have a local array. It doesn't matter what the array or how many characters you allocate to the array because it has to be finite. So for argument's sake, we'll just make it 16 bytes long. So we'll say your buffer only has 16 bytes, like that. And then we call getS and say, okay, go to the standard input file, grab whatever is in the input file or the standard input file and put it into buffer. And then we'll just go ahead and return a 0. Okay, so that's my entire program. Not complicated. All it wants to do is to read something from standard input file, doesn't even do anything with it, and then return. Okay. So what we want to do is to find out what is really going on, as far as memory allocation is concerned when we run this program. And we'll give it something that has less than 16 characters, so we can actually see the proper use of this program, what it will look like. And then we'll start to make it crash, okay, by giving it too many characters to read. Okay, so that's the program. Not really complicated, fairly simple thing. GCC dash one all, include debug symbols, generate the executable called getstir, and getstir.c is the source file. And it complains about implicit declaration of getS. And it gives you multiple warnings too. Right here, warning, the getS function is dangerous and should not be used. Okay? Then you might say, oh, so that means if people just read the warnings, then we won't have any problems. No, that is not quite true, because you can write your own getS. Okay? People can write subroutines just as dangerous, but because it is your subroutine, then GCC cannot give you those warnings because it doesn't flag it anymore. Okay, is that okay so far? Is that making any sense? Okay. All right. So what we'll do next is we'll actually go ahead and run the program. Okay, we'll say getS, getstir, and we'll just give it some input. Okay, we'll give it less than 16 bytes of input. So we'll make sure that that is the case by using all the hexadecimal digits. Okay, so there are 16 of these. I'll delete the last one because remember, the line feed character takes up one space too. So now I have 15 characters. Press the enter key. The program works just fine. Okay, it doesn't do anything with it, so there's no problem. And the next thing we'll do is to go through GDB. GDB is a debugger. And are there any questions about what a debugger is? No questions? Okay. Okay, go ahead. Sort of? Okay. So I can show you what a debugger is, because it allows you to set up breakpoints, and when the program stops working, it will give you some information. Okay. So the first thing we can do inside the debugger is we can list a program, and we can set up a breakpoint. So the B command is basically setting up a breakpoint. So I want the program to stop running at line 8. So B space 8 is to set up a breakpoint on line 8. Many of you probably know or have used CodeBlocks or something like that, which is more GUI oriented. You can do the same thing in CodeBlocks. It's just that I'm much more used to GDB, without the TUI or GUI interface. Just use command line to handle everything. Okay, so now I have set up the breakpoint, and I'm going to run the program. To run the program, it's just R, press the enter key. Now the program is waiting for the input. Same thing as last time. I'll give it all the digits except for F in hexadecimal. Press the enter key, and now the program has reached line 8, and that's why it stopped. Okay, it gives me a chance to take a look at what is in buffer. So what I'll do now is I'm going to say print what is in buffer, and hey, that's not unexpected, right? It has got everything that is supposed to be there. So this program, works okay. If I continue execution with the C, it will just run all the way to the end. The program exited normally, which is what we expect from this program. So the next thing we're going to do is, okay, what happens when we give it more stuff than 16 bytes. Okay, that's the question. What is going to happen? So we'll give it specifically a little more than that. A, B, C, D, E, F, G, H, I, J. Okay, and then press the Enter key. We still get to the return 0. When we say print buffer, it will still give us. Oh, okay. So something is lost already because the input should include G, H, I, J, and you can see that that stuff is missing. That's because buffer is an array allocated in the subroutine. So GDB is being smart. GDB is saying, oh, buffer only has 16 characters. I will only print up to 16 characters. Yep, go ahead.
So in your previous print of buffer, when it got to E, it's actually also reading the line feed character, but it's not displaying it.
Well, the line feed character gets converted into the null character according to the getS documentation, and that's why if null terminates, and when you print a string, it will automatically stop when it reads when it gets to the null terminator.
Okay, so in your second example, you got way past your 16.
Yes, it should have printed everything, including G, H, I, J, but it's not. That's because GDB is being smart. GDB knows the type of buffer being an array of only 16 characters, and that's why it's saying, oh, okay, I'll give you, up to 16 characters. Yep.
Well, shouldn't it actually print to the E like?
Nope. Because it will print the first 16 bytes, or until it hits the null terminator. But there's no null terminator until after the J.
The fact that it's actually showing you 16 characters is an indication you've got a problem.
Yeah, that's what they're basically what I'm saying.
Potentially, yes.
Because they should, what I'm saying is,
Because the null terminator is going to be the next one.
should be the 16th,
In
right?
the best case, it's the next one. Yep. So what I'm doing here is I'm trying to trick.
Should go over.
So I'm tricking GDB right now. I'm trying to trick GDB and say, hey, don't look at this as an array of 16 characters. Look at this as just an address to a byte, okay, to a character. So this time it printed out everything, right? It prints all the way to GHIJ. So now the big question is, hey, we have only allocated storage up to 16 characters, right? 16 bytes. So now the question is, I have 5 additional bytes that are stored in memory. The GHIJ and then the null terminated after this, they are stored in memory, and that's why it is being displayed. The question is, well, but I did not allocate for those 5 bytes. So they must be overwriting something. So now the question is, what is it overwriting, and will it affect the execution of this program from here on? Well, we can tell by continuing the execution of this program, and it seems like everything is okay. But that is only because we haven't stepped on anything that is important to us yet. Okay? So the next thing is, okay, without even understanding how memory is allocated in memory, what do you think is one approach from here on to go like, if I want to crash this program, if I want to exploit this program, what do I do? What is the next thing that I should do? We keep increasing, right?
Yeah.
We keep lengthening the string, okay? But that's a lot of work, and I hate work.
Well, write script for it.
So what I'll do is I'm going to use a separate terminal, and I'm going to craft the input file. So I'm going to craft the input file and go like exploit.1, okay? And I'm not even going to bother with any particular pattern. I just filled it up with stuff, okay? And the point is, this is kind of pseudo-random because the idea is I don't want it to be repetitive. I do not want it to be repetitive because, well, we'll see later, okay, why I don't want it to be repetitive. It won't give me a signature. So I'm going to save this file, and then going back to GDB, this time when I run the program, I can redirect from exploit.1. Okay, so this is how you can run the program, but instead of waiting for me to type something on the keyboard, it is taking the content of standard input from this particular file. It's called redirection. Okay? which is really handy because now I don't have to type all the gibberish over and over and over again. I can just press the enter key. It will get to the breakpoint without any problems, okay? And I can even say print and then use typecast just like last time and say look at buffer not as an array of 16 characters but just as an address of a single byte, and it gives me all the gibberish, okay? But this time when I say continue execution, it goes like, oh, I don't like it anymore. Okay, we have a problem. Okay, and it gives me the segmentation fault. A segmentation fault is basically saying we are attempting to access memory location that we're not supposed to. Okay, how are we not supposed to? Are we writing to a location that is not supposed to be written to? Or are we reading from a location that we're not supposed to read from? Or are we executing from a location that we're not supposed to execute from? We don't know. Okay, we cannot differentiate. But it does give me an address. Okay, that's one thing. That's one clue. So, what do you think we should do next? Well, maybe we should look at some of the registers. Okay, I know this is new to many of you because you have not taken CISP 310, and for those of you, and I know who you are, who have taken CISP 310. This is new also because I'm using the 64-bit version instead of 32-bit, so some of the registers have changed a little bit. Okay. So this time, we're going to do it a little bit more carefully. So we'll run the program again, but this time when I run the program, I'll put a breakpoint on line 7 right before the getS call. I'll run the program again and using that gibberish stuff as the input, but it's going to stop on line 7 first, which is great. Okay. This is before the problem. And what I'll do is I'm going to do an IR, and particularly I want to look at the stack pointer, which is RSP. Okay, so I want to look at IR RSP. SP stands for stack pointer. Okay, this is a very important concept in C, C++ programming because those programming languages make use of the stack for a variety of stuff. Okay. So this is one of the registers, and then the other register, which is also very important, is called the BP, or the base pointer. So RBP is the other register that is useful. They are usually pretty close. If you look at these two numbers, they're only off by 16 bytes. Can anyone guess why they're off by exactly 16 bytes? What is 16 bytes? The buffer. The buffer itself is 16 bytes. If you're not used to hexadecimal numbers, you might say, oh, but they're not off by 16 bytes, they're off by 10 bytes. But these numbers are in hexadecimal, which means each digit has 16 values. And that's why when they're off by 1, they're off by, well, when they're off by 1 in the second least significant digit, it's actually off by 16 bytes, not by 10 bytes. Okay? All right, so these are kind of important stuff. And then the other thing you can also do is to take a look at the stack. Now the stack grows down. In other words, as you use up more and more space on the stack pointer becomes lower and lower and smaller value. So right now the stack pointer is at location E210. So what we can do is we can just take a look, take a snapshot of what is at that location right now, or what is the whole bunch of locations. Okay, what do they look like? And we can use the X command to do this, and I can say display up to 64 bytes and display each one in hexadecimal. It's probably better to display these as long words, but we'll just go ahead and do a BX here, and we'll be using RSP as the location to look at. And it just does a dump here of the memory location content, and you can see that from 210 all the way up to 218, they're not really particularly interesting values. And then you can see that there are certain locations that have something that seems to be kind of interesting. Look at the address on the left-hand side. Okay, the address on the left-hand side is 7FFFFFU220. Okay, so just count the number of digits. How many digits will you count in that digit? 4, 8, 12. Okay, 12 digits. when you look at the memory content, do you recognize something that resembles 7F, FF, FF, blah, blah? You do. It's just quote unquote spelled backwards, okay? But it's not really backwards because it is in little endian, which means the least significant byte has the lowest address. So when you read it, it is 0000, but the leading zeros are not displayed. 7F, FF, 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 E230. That is an address, okay? You don't know what kind of address it is, okay? But it seems important, okay? Because it's an address. Go ahead. There's another address, which is here. There's a whole bunch of addresses.
No. This one that we
Okay. So it points back to a certain location, right? Okay, very good. It points back to a certain location.
So if we have the address in the front, why do we need this one?
Which one?
So if we have like a written address on the front, like a whole line, then why we have two?
This is the address. Okay, it means this byte is at location 7FFF FFFF E210 has this particular byte. So what we're seeing here is at the location 7FFF FFFF E220, we have the address of whatever is ending at with 30. Okay, but that seems important to me. It doesn't seem random at all. Is that okay? Mm-hmm. All right. So what we'll do next.
So hold on, question.
Yep. Go ahead.
So like just say you're doing this and you're not really as familiar with what exactly what exactly is it about those sequences of numbers and those things that you would say, oh, this is something of interest.
So like,
Because when you corrupt it, then what are you actually corrupting? That becomes the question. Okay? There's one more thing I want to look at. It's called RIP, or the instruction pointer. The instruction pointer is the address of where we're executing code. Okay? So the instruction pointer has a certain pattern to it. It has all the leading zeros, and then the least significant bytes are 4004 in this case. Do we see anything like this in the memory dump? 4004 or something along that line. They're off by a little bit. Okay, 4005 0F. Okay, but it's in the same region. Okay, that's the important part. It's in the same region. This is RIP bit is not rest in peace. It is a register. It's the instruction pointer. Okay, it's the 64-bit instruction pointer, which means it stores the location of the next instruction to execute. Okay, and these are return addresses. When you see it on the stack, okay, these are return addresses. It's basically saying, oh, we need to go back to a certain location. Which location are we going back to? We're going back to location 4005 0F. Okay? And there is a way, I cannot remember how, but there's a way to map memory location to line numbers in the program, in the source code. I cannot remember how, but there's a way to do it. Okay. So now what we're going to do is we will continue the execution of this program by using C. And now we get to the breakpoint. In other words, I have just read all that gibberish from the file. And what I want to do is to take a look at the registers again. So I would look at RSP again. Okay, the first one is RSP. And you will say, hey, RSP, or the stack pointer, is not corrupted. Well, it cannot be corrupted yet. Okay? It will be corrupted later, but it's not yet corrupted. Because we just returned from the subroutine. The subroutine, the call to getS is not having a problem itself, but it is setting up the memory to have a problem later. Okay? So the stack pointer is still in the same place. The question is, what is the content at that location? So what we'll do is we'll do the X command again, which is the memory dump command. Okay? And this time, what do we see? In this case, I'll just let you guys compare. I can pull this down a little bit so we can see a little bit more. There we go. Okay. The upper portion is before reading stuff from the standard input file. The second half is after reading stuff from the standard input file. One thing we can see is, hey, we see a whole bunch of ASCII codes because they're all falling within the range of printable characters in the ASCII code. The 6 stuff, 61, 69, 66, those are all lowercase characters. The 2 zeros are the space characters. Okay? So if you were to print this using, let me point out here. So instead of using BX and instead of use BC, C for character, we would have printed the content of the file. The array buffer is supposed to go from 210 all the way up to 21F, which is okay to contain the content of the file. But we went a little beyond that. Okay? We covered everything. Okay? We covered everything, including the return address. Is that okay? So the return address used to be right here. Okay? This is the location of the return address, which is 228. Okay? If you look at the blue 228, that's some gibberish here. Okay? It's not an actual return address. Yep.
How do you know that that is a return address? Did we check before? So how do you know that it's a return address? Did we check
Because
before?
the only type of location that is in the code segment that you store in the stack are return addresses. In general, okay, but there are very few locations where you have to store
Like,
a location. Yeah.
my question is like how we know that there is a return address there? Did we check before or?
Because it is near our IP, it's near the location that the instruction pointer is coming to. Yeah, it's just a little beyond that. It's in main, basically. Okay, it is in main. Okay, so now what we're going to do is we'll single step the program. Okay, we'll go ahead and single step the program. And this is all without dropping down to assembly level debugging. Okay, so I single step the program. And now we're at the end of the function f. Okay, we're just ready to execute a return statement. And then it crashed. Okay, it crashed. It actually managed. Well, okay. First of all, where is it crashing? It's crashing at location 400505. It is not in main. It is supposed to get back to main, isn't it? Okay, so that's the first thing. It's like, oh, okay, that's kind of strange. It did not get back to main, and it remains to be in function f. So the second thing that we can do is to look at the registers, because we want to look at the registers and see how they are changed this time. So now we can say, okay, let's take a look at the typical registers. Let's take a look at the stack pointer. And you can see the stack pointer is now E228, which basically means it tried to use these bytes to return, and it was not successful. Okay, it couldn't do it. And I think the reason why it crashed, quote unquote, in function f itself is because the segmentation fault is on the instruction that tries to return instead of at the location where it returned to. And that's a change of behavior from 32-bit to 64-bit code. I mean, the behavior of the memory protection scheme has changed. Okay? In the 32-bit mode, it would have tried to go to that location and crash at that location. But in 64-bit mode, it would crash on the instruction itself. The return instruction is the one that's going to crash. Okay? Which is good in a way because it doesn't give me as much clue without going on the GDB of how to tweak the code.
So basically, what you said was that 64-bit kind of like, it checks, can I go to that address? I
Right.
can't. I'm going to crash
Then
the
it
code
crashes.
that told me to go.
Right. As opposed to 32-bit where it will go to that location and then find out that it cannot execute at that location. So that's why that's the behavior in 64-bit that is different from the behavior in 32-bit. But nonetheless, these bytes are important. Okay, they actually have a certain importance. The next question is, can we then change the input file to intentionally inject a value here so it will return to vol to a place that is not supposed to return to, but the place that I want it to return to.
Yeah, why not? Define which character of the objective is.
Yes. Yep. But with a debugger, you can figure it out. Okay. So one thing you can do with a debugger, even without a source code, you can still do a certain level of hacking. So this part is a little bit more dependent on your knowledge of assembly language programming. So for those of you who have taken assembly language programming, it will sound familiar. If you have not taken assembly language programming, it may motivate you to take assembly language programming. So it depends, again, depending on how you look at it. Okay, some people may go like, no, this is exactly the reason why I want to take assembly language programming over at Sac City. Just not here. Anywhere but AR. Okay. Okay, so I'm going to quit this program. And what I'm going to do is I am going to strip the executable so it does not include the source code anymore. So we're going to say stripped get stir. So now it has no symbol table. There's no way to link back to the source code. And I'll go through GDB again, okay, just like that. And this time I will run again with, now even without the symbols, okay, no debug symbols found, there are still things that you can kind of see from the assembly code. And I cannot remember how to disassemble. Well, help. I cannot remember the command, so there's always help here. And let's see, it will be probably data. Disassemble specific section of memory. Okay, so there we go. So here's the disassemble. Okay. So we say disassemble, no frame selected, because the program has not run yet. Okay, so let's quit. There's another tool that is really helpful. It does not depend on the symbol table. It's called obj dump. Okay, so we can do an obj dump on the file on the executable, and it gives you a bunch of options. So we'll select -D for disassemble, -X to show all the headers. I'm just reading it out here. Okay, so this is -X. It displays all the header, and then -D will do the disassemble, and we'll go ahead and pipe the whole thing to less so that we can display page by page. So this is the header, and you can see that in the header there are specific locations: 400040, 400200, 40000. Those are all mapping to the space where the program is located. Okay, and these are all starting points of specific things. Now, what thing it is, I don't know, because it doesn't really tell you what it is. And then you can keep going. And this is a symbol table. Even though it is without a symbol table, it will still retain certain symbols, in here. And then we have certain names, that can be helpful. So we can kind of go through this. Now we have the actual code. These are the actual assembly code. Init is something that is called from the operating system. This is before your program gets control. This is before main. Okay? And you can see what it is really doing here. Okay? I recognize some of this already. What do we recognize? Registers. RSP. Yeah. And we also recognize forgetS, the function call. Okay? So right away we know, this is the function that is going to have a problem. Okay? So the question is, who's calling it? Okay, because whoever's calling this is going to be, is going to have a problem too. Okay? I can control where I want to go back to.
Would it be the operating system that's calling all that?
Nope, the operating system is calling the main subroutine, which is not this part here.
So this is a call from program itself?
It's called by main. Okay, this is the starting point of the code that goes on before main. This is getS itself. And this is calling the start of main, so that's not what we want. So we keep going. And this is the last part. Okay. All right. So we have to track our way backwards. In other words, we know that this is calling getS, which is what we are trying to do. So we want to find out who's going to call 400390. Now we are inside a program called less, which is a pager. So we can now search for 400390. So this is the actual location, and this is the call to that. And that is, so I'm trying to figure out, where is the actual main subroutine. And I think this is the subroutine that contains the call to getS, because nowhere else is the call to getS. So let's try to find getS. Okay, here's one. And then all of the other ones, they are basically just, this is the actual definition of getS, which is not what we want. And these are conditional branches, JBE, JE, those are all conditional branches. And then we have more conditional branches. And I think these are inside the function getS itself. And that's why we have all of these conditional branches. Okay, so I think what I suspected earlier is true. This is the subroutine, and then I need to find out who's going to call this location. So we need to look for 400390. This is the only call. This is the call to function. Basically, this is our function f. Okay. Okay. So let's go back to the main program. Because in this case, there's not much to really kind of play around in this program. Let me change the source code a little bit, so we can, kind of say, okay, but what can we do? What can we possibly do, in this case? So let's say we have, a conditional statement here, and then we have if.
There's a command right before that. SAR. What is that?
Where?
It was right before the call to that address. Yeah, it was SAR.
SAR?
Yeah.
That's a shift instruction, which is usually used to do multiplication. If you multiply by any power of 2, you can use a shift operation instead. Okay, so let's say we have some kind of instruction here, or some kind of conditional statement here, and I'm just using true here, so it is forcing that we only go to one branch. And let's also say that on one particular branch we say printf failure to log in. Okay, failure to log in. Okay, so this is just printing, I cannot log in. And this one is just confirming that authentication successful. Just like that. Bad grammar, but nonetheless, it makes the point. Okay, I'm just using the condition of 1, which is a constant, which looks really silly. But when you look at this code, there's no way that I should be able to get to authentication successful, right? Mm-hmm. Because you cannot make 1 false. 1 is always true. Okay? So now the question is, can I tweak the input file so I can get to authentication successful? Okay? So that's what I'm trying to do here. And I would try to do it without the use of source code, because you don't get the source code with most programs. Okay? So we'll go ahead and recompile the program, GCC, the whole thing, and remember to strip it. Okay, so strip, strip, get str. That will get rid of all the symbol table stuff. Okay, and then we'll go through the same thing. Obj dump -x to display all the header, -d to disassemble, and get str. Okay, and I forgot to do a pipe to less here. Okay, so we go back to the clue that we identified earlier, which is finding, okay, who's calling getS. There we go. All right, so we have a put, we have a getS here. And we'll see what else is here. Okay, we have a bunch of getS. This time we want to look at the printf or put S. Okay, so let's see if we can find printf. Nope. Let's say put S. So this is actually putting the string. This is actually displaying something. And I'm guessing it has optimized the conditional statement out entirely this time. So that's why we cannot find a call to get put S. Okay, fine. We'll change the program so we cannot optimize it out. Okay, int x equals 1. Change that to x. How's that? Think the compiler is smart enough to optimize this one out?
They might optimize it to a register, but not completely, right?
Yep. I don't think it will optimize it all the way out. So let's go ahead and recompile the program and strip and then do an object dump and look for put S. So
Actually, you know what? It might optimize it out. Some compiler optimizes it.
oh, you mean the output of the compiler? No, it doesn't say that. All right, so let's do this without stripping first because we need to make sure that this code is breakable. All right, so the 2 points of interest is line 18 and line 22. Okay, so we want to take a look at line 18 and line 22, and one way to look at that is to put a breakpoint on line 18, put a breakpoint on line 22. And this is really kind of important because this is cheating, okay? Because I do have the source code to begin with, but we can identify 2 addresses. We can identify the address of 570 and the address of 57C. Okay? And those locations correspond to the calls to printf. But it's not going to do printf, it's going to do put s instead of put string because I don't have any format characters. And GCC is smart enough to recognize that we don't have any actual format character. We can substitute printf with a put s, which is a lot more optimal. Okay. So we remember 570 and 57C, and then we go back and do an object dump this time. 40057. What again? 0. Okay. So that's the location. It is calling put s. I thought I missed that, but anyway. So the question now is, how do I force the return address to go to, I think it's the second one, right? The second one is what I want to force it to go to. It is 40057A. So I want the return address to go to, oh, I take it back. Is it a C?
Yeah.
Okay. So I want to force the return address to be 40057C instead of the other one. Okay, so this program will now be kind of modified so that I can get authenticated, even though it is supposed to be impossible to get authenticated. Are we still doing okay so far with this? Why have I lost everybody already?
Give us a concept.
The concept, yeah, the concept is the most important part. It's not the actual mechanism. Okay. Okay, so 47757C is what I want. So how do we specify, 40057C in a text file? And where do we put it? The next question is, where do we put it, right? Okay, so what we want to do is to go back to GDB. This time we just run the program. We put a breakpoint on line 7. Run the program. And we just give it A, B, C, D. Continue to put a breakpoint on line 8. Continue the program. Give it A, B, C, D. Now it stops. So what we do is we look at the stack pointer again. So we say x/64 b x at RSP. Okay. Hello, Walter.
Make sure he's not eating and drinking.
Oh,
I
okay.
was just told that somebody's in there eating and drinking. We got to make sure they're not doing that around here. He's got to put that
okay.
stuff away.
Okay, so you have to just put it away, please. Thank you.
Please, Dan.
All right. Sorry. No problem. All right. So we are going to hack this to change the return address. the return address is this one here, 400568. We have to change those to 04057C. Okay, that's what we want to change to. So it sounds really simple, but it's kind of simple. Each row has 8 bytes. So the first 16 bytes or the first 24 bytes are useless. Okay, whatever we put in the first 24 bytes is not important. But the next 8 bytes are important. We cannot overwrite. I suppose we can, because we can put zeros into the file. Because as long as they're not line 2 characters, we'll still be okay. So now we'll go ahead and handcraft a particular file to trick this program. Okay? So now we'll go ahead and handcraft this code. I'm going to use the other window here to do that. Okay? So now we go exploit.2, and we'll say 0, 1, 2, 3, 4, 5, 6, 7. And we'll repeat it 1, 2. Okay, so now we have 32 bytes in it. Because I can confirm that based on the cursor location. It's at cursor 1 right now, and now it's at cursor 32. So we have 32 bytes into this file. Only the last 8 characters we actually have to modify. There's a tool to do this. Okay, it's called hex edit. It may not be installed. No, it's not installed. If it's not installed, we can still look up the characters. So it's 4005-7C. Okay. Let's see. Oh, or I can just go ahead and install it here. Yeah, we'll just go ahead and install it. It's just a whole lot easier doing it this way. This is why I like Debian. If it's not here, it's just one command to install it. There we go. Now we have hex edit. It's a hex editor, so we're going to edit exploit.2, and we only want to modify. And we only want to modify the last 8 bytes, which would be these 8 here. And remember, this is in little endian, which means the least significant byte is the first one that we want to modify. So when we read these bytes, it's going to be 0, 0, 0, 0. They're all zeros here until we get to these 3 bytes. It's a 4005-7C. So I have just handcrafted a few bytes into the input file. Okay? So let's go ahead and save it. Control X, save. Now we go back to the program, and we run the program again from exploit, using exploit.2 as the input file. Run it from the beginning. I still have all my breakpoints, which is fine. Okay, continue. And we are ready to return now. But before we return, we want to check the memory content and see if the hack is effective. So now we go back to this instruction here and look at the hack. What do you think? Do you think it is successful? It's there, right? I have just injected the wrong return address into this program. It's returning to main, but it's returning to the wrong spot in main. Okay? So now if I continue execution again, it should print authentication successful. Okay? So we'll go ahead and continue execution. Press the enter key. It did crash at the very end, but that's besides the point. Because I was able to make the program authenticate when it is supposed to be impossible to authenticate.
But it crashed, so it's authenticated still.
Well, it's not
after the main return.
It crashed after I gained control. Okay. Which means if I want to put any actual exploit into the payload of this program, my payload would have run already. I would have already opened the back door. Okay? And as a result, yeah, this program will crash all at once. It doesn't matter to me anymore because I have already started a new process to open the back door, okay, And this program, whatever its purpose it served originally, is of no interest to me whatsoever. Because now I have my backdoor to this entire server, and I can now do further hacking because of that. But this is interesting in some other ways too, because if you think there are programs with, software detection keys and stuff like that, if you look into the source code and you can identify where it is reading in a key and it is exploitable, you can now craft it into file, into the key file, and then you can potentially make it go to the wrong place, thinking that authentication or the key is already checked.
Last week when you suggested that, you suggested that set up your own little private, like, Moodle. Is this something that you could try to play around with, or is there Moodle you can
Oh, this is entirely different because the Moodle kind of hack is based on known exploits or web serving. So you are coming in because of PHP scripts that are written in an insecure way. So this is a whole different level of hacking. This is basically hacking the executable
or like native code?
Of an executable. And this is much more valuable in some way because the operating system, the kernel, and most of the utility programs of the kernel, Apache itself is in native code. So this gives you the ability to at least look into the executables of the program, of an operating system, and basically see, okay, can I hack this? And the first thing you do is what again? Look for GetS. Look for all the bad functions that your programs are not supposed to call. And once you locate those, then you say, okay, who's calling it? Okay? If it's being called to read in a particular file, for authentication or big map to display, then you hack that file. And see if you can get the content to load into memory when it's not supposed to.
So is the send call a previous sign that's GetS?
Well, there are many, many reasons. Segfault by itself can be.
Well, I think the program works fine when you aren't using it, and then you put in an essay and then segfaults.
Mm-hmm.
Is that a pretty good sign that they're using GetS or something similar that just doesn't
It means the program doesn't do check. It doesn't really check the length of the input as opposed to the actual capacity of the array that is supposed to be to store whatever you put input. So that is the first qualification of this program being hackable. It doesn't mean that you can always get control. Just the fact that it crashes doesn't mean that you can craft something to gain control, but it is in the right direction. So it is worth looking into, if you can get a program to crash. Any questions?
What if the program is obscured or scrambled, so it's difficult to see in what order it executes?
You mean it's off-escaping?
Yeah. I can't remember what the word was.
Well, it still has to make calls, right?
Sure.
And this is based on memory content. It's based on it is you're overflowing an array and you're overwriting content on the stack. So if you change the ordering, it just makes it harder to disassemble or to decompile the program. In this case, I'm not really decompiling the program. I'm just forcing it to exceed what it is supposed to read. So the most important point is to identify GetS or something along that line.
What if it's obscured in such a way that it doesn't recall and conventional? Hey, Nate?
A question, speaking of while he's on the subject, if a program does have to make function calls, and they have to occur in some logical manner that was originally intended as a program, then how does obfuscation work? What are they injecting?
They can do it by changing the order of things, like certain conditional statements, they usually have a certain pattern, and they can kind of change the ordering so it's not as easily recognized. Oh, this is a conditional statement, or this is a loop, and so on.
I don't know, the kind of time was like our class. So we had a bit of confusion of like making something a well-formed form, and he's like, okay, if I just group these together. I'm seeing that as the same thing, but we've said if we group the wrong set of parameters, we're changing the actual logic, so wouldn't that be the same thing? If you change the order of the condition, don't you change what the
So there are
condition?
programs, that are designed specifically to alter the ordering without changing the actual meaning of the program. If you look up obfuscation in coding, there are programs that are designed to do that. I don't think they would do that much anymore because it is not very effective against
Right, which is why I asked also about the non-traditional function column.
Well, if it is done by compiler, it will still be conventional.
Right, but usually the obfuscation programs would just take a compiled program as it would and then dump out some garbage looking stuff.
Yeah, it's only garbage looking to the human eye.
Right.
Because it's still a mechanical program that is doing that process, so there's still there's still a way to unobfuscate. You just have to, read therefore that code, and then you can probably mechanically figure out, okay, this is what it usually
Police started on the
So at the end of the day, you still have to scan over the assembly dump to try and see
Yeah.
if there's some tropes that we can
Yep, it will take you longer,
And
but,
you-
but when you can read that code,
And
eventually.
you've proven to be like
Okay.
Yep.
the guiding light.
So I think that's going to be all
You
that
really
I
speak
have
up
to
to
do
my-
today is to basically just go through this process.
Yeah.
To explain how, basically how hacking is done. I cheated a little bit because I looked at the source code and used that to put in the addresses, okay? So in real life, you would have to go through the actual executable and locate those two as calls and say, okay, these two, because when you look at a press call, they would pass the parameter on the stack, and based on that, you know which one is saying successful and which one is saying failure. And then you can still be able to use the same logic on it.
What if it was a program that had a specific, like maybe there was just some signal, like maybe from the operating system, it got a timer every now and then, where it would just check to see how long it took to run. Would that have any way of avoiding it, or just crashing itself if it detected that something was wrong? There's nobody who can make programs like that except maybe like some government somewhere. Or something. Yeah, some government somewhere.
Are you saying that
That's one of the
to
things.
detect like the clock cycle of skipping?
Like if it took a minute to do a loop that should have by all rights taken half a second.
While it
He doesn't have it.
Because
Timing is not reliable because it depends on what else the system is doing, right? Sometimes it takes longer, and other times it won't take as long. So using timing as a clue that your program is being hacked, it's not reliable.
So you shouldn't expect it to try and detect if it's on like a virtual machine or if there's some breakpoints where it's
You can detect whether you're on a virtual machine through the using it. That part is not difficult because the processor type inside the virtual machine is not going to be the same as a real processor. So you differentiate that. But to detect whether the program is being hacked or has been hacked or not using techniques like this, it's difficult. Because you basically need to compare what is expected against what is not expected. But if you already know what is expected, then you already would write a code to prevent this from happening in the first place.
So
you
like
see the reasoning?
yeah, so like if it was doing checksums on the stack occasionally, like you would detect that pretty well.
Well, you would need to do a checksum before and after the call. So you have to, before the call, you basically would say, okay, this portion of the stack can be affected by this call. So I'm going to do a checksum for the rest of the stack that is not supposed to be changed. When the call returns, then you perform another checksum and make sure that the portion that is not supposed to be changed still have the same checksum. Yes, it can be done, but it is expensive because every single time you call, this whole checksum recomputation has to occur. So it can be done, it's just expensive. And
So nobody
sometimes
does.
you can't easily identify which portion of memory you're not supposed to modify. Because your getS may be getting a pointer that is a parameter of the function that you're in. So it belongs to somebody else, and who knows, whether that is legit or not to begin with. So it is difficult to find out, which memory locations you're not supposed to modify. There's certain locations like all the registers, whatever the return address and stuff like that. Yes, that no program should be modified. So you can probably do a check on those, but it will still be time consuming. Right? The program will execute a lot slower, when you do something like that.
So probably safe to say they don't have that in like StarCraft 2 or Photoshop.
Not the production version. Okay, before you get into the production version, there may be libraries they can get with, or they change the compiler to emit additional code to do all kinds of early corruption checking and whatnot.
Sure.
But none of that code is going to be in the final production version because you want the maximum performance when you are ready to use that code. Alright. So that's all I have for today. And as I said, this is a little bit, advanced, for people who have not taken CISP 310, but if you have taken CISP 310 already, you should know that at least get a basic idea of what it is about. The exact mechanism depends on the architecture, depends on what kind of code is emitted, how the stack is being used, where the return address is located, but the general idea still applies. Alright. So thank you guys. So I'm turning all of you guys into potential hackers, which is the idea. That's what I want.